Okay, next, the degree of a vertex in a graph. Let G equal to V comma E be a graph that is non-empty. That means the set of vertices is non-empty. There is at least one vertex in the graph. There may or may not be any edge, that does not matter, but vertices are there. The set of all neighbors of a vertex V in G is denoted by this symbol dg. Oh, sorry, no, this is not the notation, that's the notation for degree. Ng of V or simply by n of V. Here and elsewhere we shall drop the index referring to the underlying graph if it's clear what the underlying graph is. That is, we are writing G here to denote the fact that this set of neighbors is being considered in the graph G. Sometimes we will more simply write like this if it's understood what the underlying graph G is. So we will drop the index. Okay, now let us take one example, a simple example. Say we have this graph which has 4 vertices and 2 edges like this. So the set of neighbors of a vertex in the graph, that means if a vertex V is given, this is the set of all those vertices in the graph that are adjacent to V. So from this graph we can see that the only vertex adjacent to 1 is 2. So n of 1 is the singleton set 2. There are 2 vertices adjacent to 2, 1 and 3. One vertex adjacent to 3, that is 2, and no vertex adjacent to 4. So the set of neighbors of 4 is empty. Okay. More generally, if U is a subset of V, the set of neighbors of the vertices in U in the set V minus U is denoted by n of u. If you want, here also you can put that index g to refer to the graph, or you may just choose not to use it. So here what we are saying, instead of considering the neighbors of one vertex, we can consider the neighbors of a number of vertices together. However, when we take such a set of vertices u in V, the vertex set of the graph, we will not consider the neighbors of all the vertices in U that are in U. We have to consider the neighbors outside of U. In this example, if you, for example, calculate this, then first of all you have to look at the neighbors of 1, that is 2, but since 2 is present in this set U, we will not consider 2. We will have to look at the vertices outside U. The neighbors of 2 are 1 and 3. Among these two, 1 is already in this set, so that's not what we are considering, but we will consider 3. It is outside of this set. So this is equal to 3. Let's calculate a few more. Suppose we calculate 1, 3. Just like before, the neighbor of 1 is 2, that this time the neighbor of 1 is 2, which is lying outside 1, 3, so it can be taken. The neighbor of 3 is also 2, which is also lying outside this set, so that means here the neighbor is this. What happens if we take 2 and 3? There are two neighbors of 2, 1 and 3. Among them 3 is already in the set, so we won't consider it. We will have 1. And the neighbors of 3, there is only one neighbor 2. It's there in the set, so it cannot be considered. Let's calculate one more. The neighbor of 1 is 2, it's there in the set, cannot be considered. The neighbors of 2 are 1 and 3, they also cannot be considered, and the only neighbor of 3 is 2, that also cannot be considered. So in this case, this is the empty set. Okay. Now we come to the definition of the degree of a vertex. The degree or valency of a vertex V belonging to the vertex set of G is denoted by dg of V, or dropping the index more simply by dv, and is defined to be the number of edges at the vertex V, that is d of V is the number of elements of this set. This, if you recall, E of V is the set of those vertices that are incident on V, and d of V is the number of such edges. So for example, here d of 1 is 1 because there is only one edge incident with 1. D of 2 is 2. There are two edges incident on 2. Where shall I write? Let me write there itself, or I can wrap this part off. Keep the example. D of 3 is 1, only one edge incident on 3, and D of 4 is 0 because 4 is not adjacent, 4 has no neighbor. By our definition of a graph, the degree of V is equal to the number of neighbors of V in G. This is not necessarily true in a multi-graph. Okay. Now, according to our definition of a graph, an edge in a graph is a two-element subset of the graph. So, an edge, for example, this edge looks like this. It's a two-element subset of the vertex set of the graph. That means the elements appearing in this set are distinct. We won't have the same element. 1, 1 is not an edge, and because it's not an edge, you don't see things like this. This is not allowed in our definition of a graph. Such structures are there. They are called pseudographs, but for us, we are not considering them. And we also see that according to our definition, two vertices actually determine an edge, determine a single edge. Either they don't determine any edge, for example 3 and 4 don't determine an edge in this graph, 3 and 2 do determine an edge, but whenever there is an edge between two vertices, there is only one edge. There is nothing like this. We are not considering structures like this. This type of structures where between two edges, between two vertices, multiple edges are allowed, they are called multigraphs, which we will see in section 110. So you can see that the degree of 3 here is actually equal to the number of neighbors that 3 has. 3 has only one neighbor, which is 2, and so the numbers appearing here 1, 0, 1, 2 are just the number of elements in these sets. Okay, n of 4 is empty set whose number of elements is 0. N of 2 has 2 elements, so the number of elements is 2. So that's why we are saying that the degree of any vertex is equal to the number of neighbors of that vertex. Here you see that is not the thing. If you extend the definitions, if you call a vertex a neighbor of another vertex, if there is at least one edge, then n of 2 is still 1 and 3, but extending the definition of degree directly, like how it's given here, Here the degree of 2 should be 1, 2, 3, 4, 5, the number of edges incident on 2. And 5 is clearly, 2 does not have 5 neighbors, 2 has only 2 neighbors. So in multigraph this thing fails. A vertex of degree 0 is called an isolated vertex. One good thing about graph theory is that most of the terminology and most of the names are very natural. An isolated, here for example 4 is an isolated vertex, its degree is 0. It's isolated in the sense that it's not related to, or technically speaking not adjacent to any of the remaining vertices, it's sitting alone, that's why it's isolated. Then comes the minimum and maximum degree. The number delta of G, which is defined to be the minimum of the degrees in G, is called the minimum degree of G. Just like that, the number capital delta G, maximum of this set, is called the maximum degree of G. For example, in this graph, if we are calling this G, then the minimum degree here is 0 and the maximum degree is 2, which belongs to this vertex. It is clear that the minimum degree is related to the degree and also the maximum degree for any vertex in the graph. A graph where all the vertices have the same degree k, where k is some non-negative integer, is called a k-regular graph, or simply a regular graph. Okay, if it happens that all the vertices have the same degree, then such same degree k, then such a graph is called k-regular, or just simply a regular graph. A 3 regular graph is called cubic. For example, if you look at this graph, this is also a graph. The graph looking like a pentagram, where there are 5 vertices and edges are there. The edges are crossing one another. That does not matter. We have already discussed about those things. Each vertex has degree 2. So it's an example of a 2 regular graph. It's not 3 regular. If you take the graph K4, the complete graph on 4 vertices, then here all the degrees are 3. All the vertices have degree 3. So this is a cubic graph. This is a 3 regular graph. Next we come to the notion of the average degree of a graph. 2 different types of averages. The number dg, which is defined to be this summation dv, v belongs to v, is called the average degree of G. Average degree, because what we are doing here is that we are taking the degrees of all the vertices, we are adding them up, and then we are dividing by the total number of vertices. So that's why it's called the average degree of the graph. Note one thing, that although the definition of graph that we have given in the beginning allows us to consider infinite graphs, namely graphs where there are infinitely many vertices, but in these discussions we have assumed that, I think in chapter 8 only we are going to consider infinite graphs. In all these discussions that we have here, the graphs are finite. So this sum is a finite sum. So there is no question of, it's not an infinite series, so there is no question of convergence. It's a well-defined finite sum because there are finitely many vertices and accordingly finitely many terms in this sum. One more thing that should be noted is that in the beginning itself we assumed the graph, at least in this discussion, to be non-empty, so that there is at least one vertex, and because of that this denominator is non-zero, and that's why there also we don't have any problem. Clearly the minimum degree, the average degree and the maximum degree are related by these inequalities. How can you verify this? It's simple. Say you have this thing, no? That the degree of every vertex is lying in between these two extreme values. Now this is true for every vertex. What you do, you add all these inequalities. If you add all these inequalities, on the left hand side, how many vertices are there in the graph? This many vertices. On the left hand side you will get this. In the middle you will have that sum. And on the right hand side you will get this. Then you divide throughout by the order of the graph. times and just note the fact that this quantity in the middle is the average degree. So that's how you get these inequalities. The average degree quantifies globally what the degree of a vertex does locally. That is, both of them calculate the number of edges per vertex. In a given vertex, at a given vertex, how many edges are there? That's what the degree of the vertex calculates, and this average calculates that same thing globally. How many edges are there per vertex, taking all the vertex into consideration at once. Sometimes it will be convenient to do this directly or to express this ratio directly like this. The number of edges per vertex. Instead of considering degrees, we are straight away going to just divide the number of edges by the number of vertices. This is also another way of finding that average. Clearly, this epsilon g and dg are two different types of quantities. Okay, I should not probably say different types, but both of them are averages. They both calculate roughly the number of edges per vertex, but numerically they are different. Okay, still they are intimately related. The quantities d and epsilon are intimately related. We have okay, I needed that graph. Anyway, let's draw that again. 1, 2, 3, 4. Now the point we want to make here is that the sum of the degrees of the vertices in a graph is 2 times the number of edges. We are making a statement like this. How is this true? Say you have 2 edges here, E1 and E2, this edge and this edge. If you have a vertex that is isolated, clearly that vertex does not contribute anything to the sum of the degrees, because d of that vertex will be 0. Other vertices will have degree, but note that those degrees are actually arising because of these edges. Now if we look at this sum from the point of view of the edges, we see this. E1 contributes 1 to the degree of this vertex because its degree is 1. That same edge E1 also contributes a 1 to the degree of the vertex 2. The edge E2 contributes a 1 to the degree of 2 at the same time, and it contributes a 1 to the degree of 3. So this is the degree of the vertex 1. These two together give us the degree of the vertex 2, and this is the degree of the vertex 3. So d of 2 is 2, and that 2 is actually coming, one is coming from this, another one is coming from this. So that's why you see that every edge contributes 2 to the sum of the degrees. So the number of edges, or I mean the sum of the degrees, should be 2 times the number of edges. If you have one edge, the total sum is 2 because 2 degrees have been contributed. If you have 2 edges like what you have here, then the sum of the degrees is 4, 2 plus 2. If there are 3 edges, then the sum of the degrees is 6, 2 times 3. If there are 4 edges, the sum of the degrees will be 8. Like that it will go. So you take the double of the number of edges, then that gives you the sum of the degrees. And hence, now if you divide both sides by the number of vertices, on this side you have epsilon of g, on that side you have d of g. So this is the relationship between this average and this average. This is half of this previous average. Give me a moment, okay? Okay, now we come to our first result in this book. Proposition 1, 2, 1. The number of vertices of odd degree in a graph is even. Proof. We know that we have already seen this there. 2 times the number of edges is this sum. And this sum can be written as a sum of 2 sums. Plus Okay, now we look at this equation. It's an equation which involves integers and in fact non-negative integers. On the left hand side we have an even integer because this is 2 times number of edges. On the right hand side there are 2 integers and we are looking at their sum. In the second integer, which itself is a sum, the terms are all even integers, so the sum is also even. In the first sum, the terms are all odd integers, but this is even and this is even, so this sum also has to be even. So let's argue like that: since both this and this are even, this must also be even. Now in this sum every term is an odd integer. Now when we add odd integers, we get an odd integer if the number of integers is odd and an even integer if the number of integers is even. For example, if we are say adding these 3 odd integers, then the sum is odd, but if you bring in one more odd integer, say 9, then the sum will be even, because you can pair them up and in these pairs you will have an even integer, because when you add 2 odd integers you get an even integer. So just like that, in order for this sum to be even, and since all the numbers are odd, the number of terms in this sum must be even. So the number of terms in the must be even. Thus, and these are precisely the vertices having odd degree. Is even. To illustrate this result, let us take a graph, not that same graph, but something else. We are going to write the degrees of these vertices alongside the symbol of the vertex. The degree of 1 is 2. To distinguish the degree, we will write it within round brackets. The degree of 2 is 1, 2, 3. So 3. The degree of 3 is 4. For 4 the degree is 2, for 5 it is 1, and for both 6 and 7 it is 1. So what are the degrees of what are the even degrees? This and this 3. For the rest it is either 3 or 1. So these are the vertices of odd degree. And they are 4 in number. The number of vertices of odd degree is even. Whatever graph you draw or you consider, this is always going to happen. If a graph has large minimum degree, then it also has large average degree. Since the minimum degree is less than or equal to the average degree, and in fact you can relate the minimum degree to that average also, epsilon, which itself is related to d. It is half of d. So if the minimum degree is very large, then it will force the average degree to also be large, but the converse is not, it doesn't go in that way. Conversely, a graph with large average degree may have a small minimum degree. Because if this is large, then that doesn't say anything about the delta G. It may or may not be large. The only thing is that it will not exceed dg. That's the thing. However, vertices of large degree, let me put some ink. Vertices of large degree cannot be scattered completely among vertices of small degree, and for this the author has written this as the next proposition shows. It's about the existence of some special type of subgraph. every graph G has a subgraph whose minimum degree is, okay, so first let us say something about the average degree. Every graph G has a subgraph whose average degree is no less than the average degree of G and whose minimum degree is greater than half its average degree. I understand this part, but I don't see how this is related to this, starting from however to small degree. And in fact, it's not clear what the author tries to say here. What does it mean when he says that vertices of large degree cannot be completely scattered among vertices of small degree? It's somewhat vague. I have not been able to figure out what the author means and how is this related to this. This is a technical statement or a technical fact that if you have a graph, then it will have its own average degree. In that you can find a subgraph whose average degree is greater than or equal to the average degree of the original graph and whose minimum degree is greater than half of its average degree. Okay, and that is the proposition. If you are able to figure out the meaning of this part looking at what is being said here, then please let me know. So here is the statement of the proposition. It's the second proposition, 1, 2, 2. Let G be a graph with at least one edge, or it has been said like this: every graph G with at least one edge has a subgraph H such that the minimum degree of H is greater than epsilon of H, that average, which is greater than or equal to the epsilon value of G. So we will see the proof of this proposition in the next video. Okay, you can understand what it means. So let me tell you a little bit about the proof. In the proof, our aim will be to find a subgraph H which satisfies these inequalities. Now, I want to make the minimum degree of H large. So that means what? I have to remove vertices of small degree from G so that ultimately vertices of large degree remain. Because I want to increase the minimum degree, so I have to abandon the vertices of small degree. But one problem with this is that when you remove a vertex, the edges incident with that vertex also gets removed. Those edges contribute to this ratio positively. Positively means since E epsilon of H is the number of edges in H divided by the number of vertices in H. If you are removing one vertex of, let me take G here, then it will be more meaningful. If in the pursuit of H, I am removing some vertex from G, the denominator decreases by 1. The numerator also possibly decreases because the edges incident with that vertex get removed. So what type of vertices should I remove? How should its degree be restricted so that this ratio does not decrease? It either stays the same or it increases. So that if you can figure that out, then you can prove this. In fact, that's what we will do in the next video. Okay, so I end the video here itself. Usual things, I should not say these things again and again, but you can write in the comment section, and if you find these things interesting, then you can consider subscribing. So that will be all for tonight. This is me, Lucifer, from a mathematical room. Have a nice night.